Hello everyone, my name is Melissa.L.C and I'm presenting my satellite image analysis final project. My research question was based on the refugee influx of Uganda over the last decade. The goal of this project was to analyze to what extent their presence has changed the land in terms of land cover and natural resource use. In order to accomplish this, I needed to locate a point of interest that I knew has substantial refugee population or has experienced an important influx of asylum seekers. Next steps were to evaluate land cover change from an NDVI change detection map from years 2015 to 2023. Then validate random stratified samples from the threshold change map and collect Earth Online. The last deliverable would consist of determining if these techniques were reliable in order to create a new land cover land change map in the future. The area of interest is central Uganda, with points of interest including 3 refugee settlements, Ramwanja, Kayaka-2, and Nakavale. The refugee population in these areas of interest are approximately 425,000, and that is at this current moment in 2024. To analyze change for this project, I used Google Earth Engine using Landsat 8 imagery in phase 1 and Collect Earth Online using NDVI Planet Public and Mapbox imagery in phase 2. Methods used in phase 1 consisted of creating 2 cloud masked median composites, one from 2015 and one from 2023. I then created an NDVI threshold change detection map with these 2 cloud masked composited images. Next, I created random stratified samples. In total, there were 50 change samples and 50 no change samples. These samples were exported in CSV format from the newly created GEE assets into Collect Earth Online and into my validation project. Once all 100 samples were validated with truth data, they were exported and put into a joint Excel where I performed a confusion matrix assessment. Creating the threshold change detection map consisted of making masked composited images, which you can see here, with some spectral examples from the Nakavale refugee settlement delineated with a red pin. The purple pin represents an area within the settlement that has undergone land change. Here is an example of the change detection map from a location at the Kayaka-2 settlement that has experienced change in vegetation loss. The threshold change map was a 0-1 change map where anything that showed equal to or more than a threshold of -100, it was computed as change, represented by a 1, and anything with less than a threshold of -100 was computed as no change and was represented by 0. The red areas you see here on the second map represent all areas that have experienced change that were extrapolated from the NDVI composite change detection map. The ground truth validation of stratified samples was processed in Collect Earth Online. This did come with some of its own challenges, as this program requires that you reformat your CSV and shapefiles from GEE to agree with their data, and making sure to name all of your data columns correctly because they are named differently in GEE assets. There are example downloads you can copy when you get to this part of the project creation, and I highly recommend looking at their formats to save you hours of frustration. As my goal for this project was to determine change, the only important data was the response to my main question card, was there change, as you can see here. And this was the only data I would be using to validate these points with the original GE sample points in the confusion matrix. However, having documentation of what the land cover was before and after will be helpful when revisiting this project in the future when a more thorough analysis can be done. And here is an example of the data collection and the methodology of what you must do to assess the change. This location experienced vegetation loss. The confusion matrix. Why are these outcomes pertinent? I wanted to know if both program labels agree. So the producer's accuracy, which is the reference points from CEO, Collect Earth Online, was 48% accurate in agreement of change and 47% agreement in no change. whereas the user accuracy, which are the predicted points from GEE, had 62% accuracy for agreement in change and 34% agreement in no change. Although the user accuracy is higher, I'm not convinced that this is a more accurate method, being just using the GEE analysis. The major challenge with the confusion matrix assessments are that there was a lot of human error to account for in the Collect Earth online point validation. This stems from me not being entirely familiar with the actual landscape of Uganda or the vegetation and the poor quality of the satellite imagery available for this part of the world. Therefore, it would be interesting and pertinent to redo this data validation after taking a trip to Uganda and seeing if the results come back in more agreement. After completing the confusion matrix, I found it helpful to go back and verify that the stratified samples were well dispersed. In this case, I think they were, but creating more samples would give us more data to validate, which would be useful in future validation runs. Key takeaways are that yes, change in vegetation loss has occurred between 2015 and 2023 in the areas of interest, and using the methods I shared with you today was still useful in detecting change, even though the confusion matrix does not agree. So in order to create a strong change detection analysis, it is vital that one has thorough understanding of natural environment, by either being there themselves or extensively researching the vegetation and other imagery. This change detection map can still provide to be useful, as it will help target areas in the settlements that could benefit from the most from land restoration, regardless if we cannot use this data yet to create an accurate land cover land use map. Well, this concludes the presentation today, and I appreciate you all for watching, and I wish you all a happy end of the term. Thank you.